Great. So welcome everyone to the session. And the next 50 minutes, we'll be talking about 3 things that you don't want to store in a database, but sometimes have to. My name is Gianluca Sartori. I am the founder at Quantum Datis and the Data Platform MVP. I've been working with SQL Server for a very long time. Currently, I'm working as a DBA at a famous Formula One team in Italy. If you want to read my blog, you can find it at spaghettidba.com, and my handle on Twitter is @spaghettidba. Great, so what's the agenda for today? First of all, we're gonna have a look at the rules in a relational database, and then we will see why some types of data don't really fit well with these rules. And we'll talk about logs, pictures, and entities with dynamic attributes in a database. And we will see what are some alternatives for saving them in a relational database. Okay, so let's first discuss the rules inside a relational database. We've been working with relational databases for decades now, and it turns out they work pretty well with almost all types of data. And with other types of data, not so much. And the problems start when we are dealing with data that violates the rules inside a database. And in a relational database, the rules are called normal forms. Well, we have mostly 3 normal forms. There are more, but these are the main ones. The first normal form says that every entity in a relational database needs to have a primary key and then only atomic attributes. So this means that we cannot have attributes that we can break down into smaller pieces. Second normal form says that every attribute depends on the whole key. So if we have a table with a compound column, we cannot have attributes that depend on a subset of the key. The third normal form says that every attribute depends only on the key. So we cannot have attributes that depend on things other than the key. So these are the rules for working with relational databases, and we will see why some types of data don't fit well with these rules. Let's start with the first one. So logs inside a database. Well, let's have a look at what we do with logs. Why do we have logs? We have applications that perform some task. Hopefully, they do that correctly, but sometimes things go wrong. So we rely on the messages produced by the applications and stored somewhere to do some types of troubleshooting, or we can do some analysis on the behavior of the application by summarizing the logs produced by the application itself. So how does this work? While the application is working, produces these logs, and we can write these logs somewhere. Usually this is a synchronous process, and most of the time, the application doesn't go back and read the log data, and it's only written and never read again. We go back and read the logs when we need to do some troubleshooting. So we had an error occurring, and we need to read the messages around the time of the failure. And this usually happens with a sequential read. So we start reading the log, we find the timestamp that we're interested in, and we read from that point on. And other things we could do with the logs, we can analyze these logs to produce some analysis of the behavior of the application. So we group on some attributes that come with the logs that describe the behavior of the application. Another very important thing that we do with logs is we don't retain them forever. So we apply some retention policies. After a meaningful amount of time, we delete the logs we're not interested in anymore. So this could be 6 months, 1 year, but something that makes sense for the application. Okay, so how does this fit in a relational database? Well, not so good, it turns out. It's not really compliant with the first normal form. We store the logs inside a huge log column. This is a nvarchar max column, and this is very big, and we're not interested in the message in its entirety. When we research messages, we usually do that by searching for parts of the message, and this ends up in queries like this, where message like something we're interested in the message itself. So this means that we're not treating this data in a first normal form compliant way. Another thing that doesn't really make this data suitable for a relational database is that it's not transactional data. We don't really need to store logs in a transactional way. We don't need to have transactions that involve multiple rows of logs or row logs with other rows of different tables inside the database. But unfortunately, transactions is not something we can opt out of in a database. Even inserting a single row in a database is a transaction. And this is something that that becomes a problem when we have to apply the retention policy. So when we need to delete many rows from the log table, when we have to delete millions or even billions of rows because they are not relevant anymore, this is something that makes the transaction log of the database extremely big and can become a real problem. So we are forced to delete in batches and take countermeasures to avoid this becoming a problem. Another thing to take into account is that logs need to be written even when the database is not reachable. The database is just one part of a complex application where we could have a web server, an application server, services, and so on. And the database is just a small part of the whole picture. When one of these parts is not capable of reaching the database for logs, we cannot have the log messages stored, and this makes troubleshooting even harder. Also, there is no benefit in saving logs inside a database. There is no killer feature inside the database that makes it a good choice for storing logs. So there is nothing to gain and a lot of pain. So why? What are the alternatives for storing logs? Files. Files are a great alternative for saving logs. It's easy to write to files. The performance is really good. There is no overhead coming from the way relational databases save the data. Inside SQL Server, everything in a table needs to be stored into 8K pages, and then we need to save this into extents, and this goes into files. This is all unneeded overhead when we are dealing with logs. Also, it's easy to read the log data when it is stored into files. All we have to do is go where the file is stored and use something very low tech like a text editor or a log reader. Also, it doesn't have to be interpreted from binary format. This is immediately readable by a human being. And also for reading and analyzing this data, there are tools that are great for this, from the simplest grep that searches for strings inside the file to more complex solutions like log parser. This is a small tool from Microsoft that is capable of reading different formats of log, like CSV or logs from IIS or other applications. And it is capable of running SQL queries on top of plain text files. So it combines the simplicity of simple log files with the power of SQL. Also, for deleting logs, files are great. You just have to point at the file and delete it, and the deletion process is almost instantaneous. It doesn't have to write transaction logs and things like that that only get in the way of getting the work done. If you have to do more complex analysis with your logs, there are some alternatives like specialized logging applications. They are mostly based on time series databases like InfluxDB or Elasticsearch. These are databases designed to incorporate advanced features for storing the data efficiently with partitioning and sharding and retention policies built in. And also these tools are great for analyzing your logs. So it's easy to run analysis queries on top of these logging platforms. So with all these downsides and all these alternatives, why do logs still land in a relational database? Sometimes this has to do with laziness. Sometimes this is an easy button for storing the data in the same way that we store all the other data in a database. Some of the possible reasons for doing this are taking advantage of SQL, the power of SQL for querying and analyzing logs. And sometimes this happens because we can leverage some other features of a relational database, like high availability or replication or the backup. Okay, so what are the main challenges when saving logs inside a database? This mainly has to do with the high cardinality of log tables. Sometimes, most of the time, we are dealing with tables that hold millions or even billions of log entries. And dealing with just a handful of rows doesn't really pose any challenge, even if it's not the correct way of storing this data. But challenges happen when we have high cardinality objects like log tables. So this has to do with storing the data. Having this data sitting on a disk, tables like this can end up eating a lot of disk space. Also, querying this data poses some challenges because it needs to read a lot of pages from disk. And as we said, applying the retention policy on big objects like this is something that doesn't really cope well with the huge amount of the transaction log that is produced from delete operations. Okay, so what are the possible solutions for storing this data inside the database? It all comes down to choosing the correct storage, the one that gives us the best performance. The storage inside a SQL Server database means we could have heaps or clustered index. Well, a heap is a non-ordered table which doesn't have a clustered index, so the data is not stored using a particular internal order. In a clustered index, we choose one of the attributes of the log, which is usually the log date, and we use it as a key to sort and store the data inside the clustered index. What are the alternatives? We also have compression features in SQL Server that could help us with big objects like this. And also we have column store that offers other features for compressing the data in an effective way. And also we have partitioning that can help us with the retention policy. Let's see how we can combine these features to get a sensible solution for storing logs, an almost sensible solution for storing logs inside the database. Okay, so we have some databases here. We have one for the logs, one for the pictures, one for the dynamic attributes. We will start from the logs database, and we have some tables with different alternatives here for saving the data. So we have page compressed data, column store data, and heaps and clustered indexes. Let's see how we can make this work. So first, I'm going to open this file, and this script describes how we got to this point. I created a log table inside this log database, and I populated this table with a 26 gig file that I downloaded from internet. There are some samples to download, and this file in particular was the biggest I could find. And I will use this table to populate other tables with different types of storage. Well, this script takes care of creating a view to analyze the disk space, and then a couple of tables to record disk space and time taken to populate these tables, and also store procedures to record this data. It's not really interesting. I'm not going to show you the code itself. You can download it and have a look afterwards if you're interested in this. The important part is having a look at the right performance in terms of disk space and time taken. So first I'm going to run a first test to create a heap with 1 million rows. And what happens here is I have a table, a heap table, and I populated this with 1 million rows. I will do the same with a clustered index, and this time it creates a table with a clustered index. So this time we have a clustered index here. And again, we insert 1 million rows. So if you repeat this for 2 million rows, and then 5 million rows, and then 10 million rows, and even 50 million rows, we can see how this performs in terms of space used and time taken. So let's have a look at that. And we have some charts depicting this. So in terms of space used, it doesn't really change much using clustered index or a heap. It's pretty much the same. In terms of time taken, a heap is quicker to write to. We can see this the most when we're dealing with 50 million rows. Writing to the clustered index takes more time. But if we compare the performance between the two, we can see that reading from a heap, which usually happens for a time range, is something that takes some time. As you can see, it's taking some seconds. Okay, it's taking 10 seconds. We can stop it. If we repeat the same on a clustered index, it's almost instantaneous because we have a clustered index on the date column. So the time that we spend populating this table organized as a clustered index is well spent because it's time we regain when we query the data. Okay, so what else could we do to make this even better? We could compress this. We can use page compression. So I will do the same with page compression for 1 million rows, 10 million rows, 5 and 50 million rows. And we can have a look at how this works. And compressing uses less disk space as expected. So it is a good way to compress the data, but it takes more time. Again, we don't insert millions of rows in a single batch. We usually insert one row at a time for logs, but the time taken for page compression is non-negligible. Again, we are reading less pages when we read back the data, so it is time well spent. And what else could we do?
Gianluca, there is a question.
Yes.
Martin is asking, do you think of a GUID as a key to achieve maximum insert performance?
Sorry, say again, please.
Martin's asking if you thought of using a GUID as a key to achieve good
Okay,
performance
so
on
using a
incidents.
GUID doesn't really make sense for logs. It's something you will never use for querying your data. So using one of the attributes that you already have in the logs, like the log date, makes more sense because it's the attribute you will use to read back the data when you have to. I hope this answers your question. Okay, so what else could we do? Compression, we have seen that page compression is beneficial. So we could also use column store compression. Column store means that all the columns are saved independently. So instead of saving all the rows as a whole, we break down this in single column, and each column is saved by itself. And this is very beneficial when we have a lot of repeating data, which is something that happens in logs. As you can see, we have this level column that is repeated a lot of times, and the type column is repeating a lot as well. And even the messages are repeating many times. So compressing these columns independently could be a good choice. So we can rebuild the test table with a log table using column store compression. We have two types of column store compression. The regular column store that simply saves columns independently, as we said. And we have column store archive compression that, on top of the regular column store compression, also applies gzip compression, which is something that, again, makes sense when we have a lot of similar data with lots of similarities. So rebuilding this for the 1, 2, 5, 10, 50, and even 100 million rows is something that we can investigate in terms of time taken and space used. So let's analyze that. And as you can see, non-compressed is much bigger than compressed with column store or column store archive. Column store archive is so effective that it almost disappears from the chart in terms of space used. 50 million rows or 100 million rows uses roughly the same as 1 million rows on compressed. So it's very efficient in terms of compression. So we can save billions of rows using column store compression and column store archive compression. In terms of time taken, it is much smaller, the data we are writing, so it is more efficient even when we write the data. So now that we have sorted how to store this data efficiently, all we have to do is understand how to deal with deletes. So the way we can do that is by using partitioning. And partitioning helps us here because we can delete all the partitions once the data goes out of the retention window. So in this case, I'm partitioning for dates. I'm creating a partition function for all the data I have in my sample table. And I create a partition scheme based on the partition function. It doesn't really make sense to partition on different file groups, so we can save everything to the primary in this case. And one thing we can do is partition the table by creating the clustered column store index on the partition scheme. And one interesting thing we can do is we can have different compression policies for different partitions. So we can have the cold partitions saved with column store archive, and we can have the hot partition, the one we are still writing to, compressed with column store compression. The new data will be saved to row store temporary storage, that will migrate to the column store compression when we maintain the indexes, and we can decide to reorganize the second partition, keep the hot partition with column store compression, and move all the others to column store archive. So this is an effective way of storing this data. When a partition goes out of the retention, we just need to drop that partition by switching that out. Okay, so maybe a database is not a great choice for using for storing logs, but column store, when the data repeats a lot, is a great way of storing logs inside the database. Be careful if your logs are big. In this example, the logs are 8K characters, but when you have bigger messages that need to be stored in nvarchar max columns, that is lob data, and column store is not supported on lob columns until SQL Server 2017. So you need to choose the correct version for that. You can use partitioning to compress the older rows, and partitioning to switch out all the data. And don't try to delete rows on compressed segments in column store indexes, because column store doesn't like deletes. It will only make your data bigger and not smaller. Okay, so if we don't have questions, we can move to the next topic, the second bad idea of the day. So storing pictures inside the database.
Sorry, we have two questions, Gianluca.
Let's go.
First one, what would be your approach to partitioning and compressing an existing log table that is several terabytes in size?
Okay, my approach would be to move all the data to a flat file, and then import back the data using something like SSIS. Compressing existing data using column store may not be a great idea in terms of a transaction log occupation. So I would do it by exporting somewhere else and then importing back the data.
Okay, thanks. And the last question, how big or what is the effect of partitioning at the query side? Is it noticeable, for example, slower than with
yes,
partition?
So one of the benefits of using partitioning is that when you query the data for something that is included in the partition key, will produce partition elimination. So if we query for a time range that goes into a single partition, the other partitions will not be even touched. So it is beneficial. It is very beneficial for that.
Okay, great. Thanks. No more questions. You're good to go. Thanks.
Thank you. Okay, so second bad idea of the day, storing pictures in the database. Well, actually, it's not only pictures, it's binary data in general. Pictures is just a very common example of this. So how does it work? What we do with binary data? The type of work we do is we use the database as a simple storage for this binary data. So we write once, probably never touch the binary data again. And the data is not used by the database itself. So it is passed to the client application or the web server that streams this data to the client. So we're using SQL Server as if it was a file system, which is not. So as we said, for logs, pictures don't belong in a database. It's not transactional data. So we don't need to save pictures in transactions with other data that is sitting in the database. And if you have a big table with lots of binary data, with lots of lob data, maintaining indexes on a table like that will make your transaction log explode. And again, same for logs. There is no killer feature in the database that will make working with pictures a good fit for a SQL Server. The data has to be broken down into pages and extents, and need to go to allocation units. And for lob data, this goes to lob allocation units, which are separate from the regular in-row or overflow allocation units. So it's more work for the database for no gain. And the throughput obviously is poor. So what are the alternatives? Turns out that storing files in files is a great idea. It's easy to write to, so the performance doesn't incur in the overhead of pages and extents. And the data is available even with the database is offline or unreachable. It's easy to visualize and edit, same as we said for logs, and easy to update and delete. Just work with the files where they are in the file system. There are some alternatives when you need to leverage some more features. There are specialized object storages, especially in the cloud, like Azure Blob Storage or Amazon S3. And honestly, all cloud providers have a solution for this. And if you need to do this in on-prem, you can leverage some features from storages like NetApp, or even others have a solution for this. This is usually a good choice when you don't only have to store the data, but you also are interested in advanced features like analytics, or need to retain history or versioning of the binary data, or you need to distribute the data geographically, or have to leverage some of the scale-out capabilities of cloud platforms. So why does this data end up in a relational database? Again, the reasons are, in my experience, the same as for logs. So if somebody's pressing the easy button, you treat the binary data as the rest of the data without having to learn any new technique or technology. But sometimes this happens because we need to leverage some features from the database, like high availability or replication. Well, replication with binary data has horrible performance. Or backups. This is more a problem than a feature, because the binary data contributes to the backup size. So what are the challenges with saving binary data in the database? Again, this has to do with scalability. So if we're handling a few hundred, 1,000 elements, doesn't really make a difference. But when we are dealing with millions or billions of files, the database really scales poorly. So reads and writes need to incur into the performance penalty of dealing with pages and extents and so on. So the overhead of the relational database. If you have a big object with binary data inside, index maintenance is virtually impossible. You cannot touch those objects. Rebuilding indexes on a table with billions of binary rows inside is virtually impossible. And also the binary data contributes to the backup size. So when you back up all your binary data, the backup will contain all of that. So bringing back the database from a disaster will have to read also all the binary data, and will make your restores slower, and even your backups will be slower. So what are the possible solutions? Again, we have to choose the right storage. We have seen with the logs that we have different options here. Let's see how they behave with binary data. And we will do that with a demo. So again, let's bring back Management Studio. And we have some scripts. So we're going here. So this time I also have a PowerShell script. So what I did is I created a table here. It's pictures big and pictures small. And I populated these two tables with data from my downloads folder. So I uploaded all the data between 1 kilobyte and 1 megabyte in the small table, and I uploaded everything between 1 meg and 1 gig in the big table, and I will use these tables to populate the other ones. So I created different tables. Let's see how this works. So first of all, I populated a heap table. We have seen that heaps are clustered index. That doesn't really change much. So I created one with 1 million rows, and I tried to insert 1 million pictures, and it didn't even finish. I stopped this after several hours. I created a pictures big, and I populated this with 1K rows. So it took 15 minutes to insert 1,000 rows. So I tried the same with page compression, and it doesn't really change much. It's 16 minutes versus 15 minutes. Why? Because compression doesn't apply to lob allocation units. So page compression doesn't even try to touch the binary data, and it wouldn't be beneficial because nowadays most of the binary formats are compressed internally anyway, so it wouldn't really make a lot of difference. Okay, so enter one feature in SQL Server that is called file stream that could make a difference. Using file stream, the data bypasses the storage from SQL Server. So the data is not stored into pages and extents inside the database, but it is saved as files inside a folder in the data in the server. So every row in a table that has the file stream attribute on a binary max column is saved as a file on disk associated with a GUID, and that file is read when the contents from this column are read or written. So using file stream, we bypass the overhead of the relational database of pages and extents, so the inefficient storage, and we can obtain better performance. So writing 1,000 rows takes 10 minutes instead of 15 minutes using file stream. And also, if we try to do this for 1 million rows, which couldn't finish for the non-file stream, so regular storage, it takes a couple of hours. So it's much more efficient compared to the regular storage of SQL Server. So this is what I suggest for storing pictures. So wrapping this up, file stream is what delivers the best performance. One thing to be very careful about is the NTFS performance, so the performance of the file system itself. When you have millions of elements inside a folder, all of them become a single file, so the performance of the file system is critical. To make it perform better, you have to disable the 8.3 naming. So it's an old naming that comes from the DOS days. And you have to disable indexing on the file system and the last access attribute. All of this can be performed from commands from the operating system. So you have a command for that. You'd better select the dedicated disk for a file stream and choose the correct cluster size that handles the typical size of your binary data correctly. Also, set up exclusions for antivirus and anti-malware solutions. This can end up slowing you down quite a lot. If you also want to skip the TDS overhead, you could stream the data directly from an SMB share. So SQL Server has the ability to bypass TDS, which is the network protocol for SQL Server, and you can read and write directly using the SMB share set up by SQL Server using FileStream. So this gets you even better performance. So if we don't have questions, we can move to the last bad idea of the day.
Yes, there's just one question. You got 10 minutes left, and the question is, when would you use a file table rather than a file stream column?
Okay, so file table is again a file stream with more features, but usually these features have to do with analyzing the data that you have in the file tables. So you can set up filters for analyzing some particular formats in the file table. And I wouldn't do that unless I need this analysis capabilities.
Okay, thank you. And that's 10 minutes left.
Thank you. Okay, so moving to the last bad idea of the day, dynamic attributes in the database. So dynamic attributes usually pop up when it's hard to identify all attributes at design times, or even impossible to do that. Some examples of this are CRM applications, when we have dynamic attributes to record on our customers, and it's not possible to know them at design time of the application. So if we think of the normal forms, there is no way to design a database correctly following the normal forms when we don't know all the attributes at design time. So we have to rely on some implementations that violate the three normal forms. Let's see what are the alternatives. We could use some databases that don't suffer too much when dealing with dynamic attributes. And these are usually document databases like Azure Cosmos DB or MongoDB, Amazon Document DB, or Elasticsearch. These databases can deal with dynamic attributes more sensibly than SQL Server does. And we still find this type of solutions in a relational database. It looks smart to save this kind of data in a relational database, but actually it turns out it's not. And what are the possible solutions? We have the entity attribute value design, which violates second normal form and third normal form. Or we have solutions that violate the first normal form, like saving dynamic attributes in XML or JSON. So we have a column with XML or JSON inside, and this is a clear violation of the first normal form. We save something that can be broken down into smaller pieces, like the attributes of the JSON. Another possibility is using sparse column. This is a technology built into SQL Server that allow us to create columns that with the sparse attribute that deal with lots of nulls in an optimized way. And what we achieve is generic attribute names that can be given a meaning at runtime. Let's see an example of that. So we can go to the last demo. Okay, so let's have a look at what we have here. We can create an orders table, which is a normal table with static attributes, and then insert some data. If we insert 1 million rows in the orders table, we can, it takes 4 seconds. If we use an entity attribute value design, we can create an attributes table that contains the list of the dynamic attributes we want to store. So in this case, we're saving the ship date, or it can see rate ID, online flag, stuff like this. And all of these can go into the attributes. So each of these is a row in the attributes table. And then we have the attribute values table. In this case, the entity ID is the ID of the entity. So the order ID will go into the entity ID column. And the attribute ID is the ID from the attributes column, attributes table itself. And the value will be the value of this combination of the entity and attribute. And it will need to be a generic data type. So in this case, an nvarchar 4000. So even if we're saving dates or numbers into this value, we will have to store this in a single column that doesn't know how to store the data. So in terms of performance, if we insert 1 million dynamic attributes, we have 10 attributes to store. So each of this becomes a row. So 1 million attributes becomes 10 million rows. And it takes 1 minute to populate all of this. Another downside to this is we cannot have check constraints and proper data types on this design. So it's really, really a bad idea. So what else could we do? When we need to read the data, it's by rows. So the attributes need to be transformed from rows to columns. And this can be done with a pivot of an operation or with a crosstab like this. So we summarize on a case expression like this, and we extract this data back from rows to columns like this, and it takes 14 seconds to read this data. So the alternative is using sparse columns. So what we do is generate a table with attributes that we do not know how to name at design time, so they will have generic names, but it will be the application to assign a meaning to each of these columns at runtime. So we can have a date attribute 1, string attribute 1, and integer attribute 1, and so on. And all of these can have a proper data type, and they are all decorated with a sparse attribute that improves the performance of storing this data, the efficiency of storing this data when we have to deal with a lot of nulls. So if we use this design and we insert into the order attributes 1 million rows, it takes 3 seconds. It's just 1 row for each set of attributes. We don't have to transform it into rows and back to columns when we read it. So even the performance when reading the data, it's 8 seconds compared to 14 seconds. So this design is one of the possible ways of dealing with dynamic attributes. So wrapping up, there is no place in a relational database for dynamic attributes. XML and JSON violate the first normal form. So we're trying to fit a square peg in a round hole. It's not the correct solution for this. So you should really use something different from a relational database. The worst design for this is the entity attribute value design that has generic data types. So this means no foreign keys, no check constraints, and multiple accesses to the same table to read multiple attributes. The sparse columns design is not too bad. And the only downside to this is we have to assign a meaning to each column at runtime and not at design time in the database. So to close, if we don't have any questions, when storing data in a database, you need to follow the rules, and the rules are called normal forms in a relational database. If you ignore them, you will enter a world of pain. So if you have questions, I'm here to answer them. Please fill the feedback form. It's very important for the organizers and for the speakers. And if we don't have time now to answer your questions, please shoot me an email and I'll be more than happy to get back to you as soon as possible.
Yes, there is one question.
Okay.
Have you actually witnessed a rewrite of dynamic attributes in the app? I guess this is quickly turned down because of the effort involved.
Yes, I have seen many applications that try to use the entity attribute value design. And I will not name names, but even big applications, especially CRM applications, run into this type of design. It's very unfortunate and really has horrible performance on the database.
Okay, great, thanks. Doesn't look like any other questions in the audience, so yeah, right on time. Thank you very much.
Thank you, and see you next time.